If you did the wave behavior activity, you took a look at how waves behave, first of all, when they reach the end of a medium, and that depends on whether it's a fixed end or a free end. And also we looked at how waves act when they reach the same spot on a medium. And that's called superposition, how two waves interact with each other when they meet one another. Okay, so we're going to talk a little bit more about superposition today. That can also be called interference. So the general term for waves interacting with each other is interference, and then superposition is what we call it when we're adding two waves together. And that can happen in a constructive way, where waves add together, or a destructive way, where waves subtract from one another. So we're going to take a couple looks at how that works. So we've got a few mediums here. So let's look at what happens when we send, let's say, a square wave. This is square wave, and we're going to call it number 1. And it is moving this direction. And we're going to take another square wave of exactly the same size, and we're going to call this square wave number 2. And it's moving this direction. Now, when they reach the middle, let's think of these as energy levels. Okay, so at this point over here, this height is an energy level of 1, let's say. So both of these things have an energy level of 1. They're transmitting energy. That's what waves do. And when they reach the middle, that level 1 energy from one side and the level 1 energy from the other side, they reach the middle, come together, and together they create a wave 1 plus 2. This has an energy level of 2. Okay, so that's what's happening. The energy that each of the waves is transmitting reaches the middle, and when it's in the same spot, you have just twice as much energy. You have the energy from one wave and the other wave just put together. And then, after the waves have reached the middle, after they have interfered with each other, then they will continue in the way they were moving. And so wave number 1 is right over here. And it is moving this direction just like it was before. And wave number 2 is over here. And it is moving to the left just like it was before. And both of them are back at energy level 1. That's what we would call constructive superposition, when two waves meet in one position, interfere with one another, and their energy adds together in a positive way. Now let's look at destructive interference. So let's say we have wave number 1, which now has a height of 2. And it's moving to the right. And then let's take wave number 2, but instead of putting it on the top side, let's put it on the bottom side. And it has a height of 1, or you could think of it as negative 1. So this would be an energy of positive 2, and this would be an energy of negative 1. And so you can imagine what's going to happen when they interfere with one another in the middle. So when they reach the middle, you've got an energy of positive 2 combining with an energy of negative 1. And so in the end, they end up combining. This is 1 plus 2. Oh boy, you're not going to be able to read this. This is energy, this is wave 1 plus 2, both of them together. And now it has an energy level of positive 1. Okay, that's how superposition works. That's how destructive interference works in this case. Now, after they have reached the middle and passed through one another, now we have the same thing happening here. That wave number 2 is still moving in the same direction it was before. It's not like they bounce off each other. And wave number 1 over here is also still moving in the same direction it was before. So you don't often see square waves like that naturally in the wild, you would see more rounded waves, right? If you've ever been to the beach or to the ocean, you kind of know what ocean waves look like. But if you are involved in electronics in any way, then you may also know that you can create a wave of a whole bunch of different signal shapes. Okay, and that's more useful when you are working with electronics than if you're just describing waves out in the universe. Okay, and so we're going to add some odd shaped waves together and see what it looks like. Now for me, this matters because I play guitar, and when I'm playing electric guitar, I can create different effects with different wave shapes like this. Now I don't actually have to create the wave shape myself. It's already programmed into my effects electronics, and so it does it for me. But here's how it works. Let's say we've got a triangular wave like this and a square wave like this. Now you might say that's a rectangular wave. Yes, but its wave type is a square wave because it's got square corners. So when you add these two things together, here's what we're going to look for. In the area that these two waves overlap, this one over here, we have to add the heights of the waves in those regions. So this blue wave over here, it has a height of -1. So we're going to look at this triangular wave, and in this region over here, we're going to add a height of -1 to it, or we're going to subtract a height of 1. So I'm going to look right here and say that has a height of 1 right now, but I need to subtract a height of 1 from it. And so that gets me right here. And then I'm going to look at my next grid point. This has a height of 2. I need to subtract 1 from it. And so that brings me here. And then this spot, it used to be 1. Now it's going to be 0 as well. Okay, so now if I follow my wave, it started here, goes to this point right here, and then it has to drop down to where its new height is because the blue one was added. So it drops down to here, and then even I could keep making dots for all of the points in between here, but I think I can probably figure out what the transition is going to be between the two. But still, let's look right over here. This has a height of 1.5. I need to subtract 1 from it. That gets me to 1/2. And you can see that that's exactly what would happen for the rest of these points in between the two. And so it's going to just end up being connected like this. And then it will be connected like this on the way down, back up to here, and then down this way. And so the wave combination, the combination waveform that you'll find from this triangular wave and this square wave looks like this. Okay, it's kind of a puzzle. Now let's do the second one. So in this region of the square wave, of the red square wave, it's not interacting with the blue sawtooth wave at all. So this is just going to be exactly like it is. There. It's unaffected by the blue wave. Then the overlapping part is this part right over here. So for this part, we're going to have to figure out how do we add these two things together. But for this region of the blue sawtooth wave, it is not interacting with the red wave at all. So it is just going to remain exactly like it was before. Just like that. Now I need to figure out what do I do with these two. So for me, it's going to be easiest to look at the red one as a +1 and this blue one as kind of what I'm adding to. So I'm going to take this blue shape and add 1 to it. That's it. Because I'm adding an energy level of +1 because of the red square wave. So I'm going to take this blue one and just move the entire thing up 1. Okay, and so it went through about over here to over here, and so it looks like this. Okay, and there's my new combination waveform. Now the last thing that we're going to do is try to combine two of the same wave as they move together. Okay, so we're going to look at these two waves moving at 10 meters per second toward one another. And we're saying that one block is 10 meters, not 10 meters per second, just 10 meters. So if every second these waves are moving one block, where will they be at 4 seconds? Where will they be at 5 seconds? Where will they be at 6 seconds? Okay, so what I'm going to do is draw where each of them is going to be, and then after I've done that, draw the combination waveform. So at 4 seconds, this leading edge has moved 4 spaces. 1, 2, 3, 4. So it's going to start here, and it has a wavelength of, well, this isn't its actual wavelength. Its actual wavelength would be up, down, and then up again, right? But we're going to say 4 is the length of this wave. So 1, 2, 3, 4. This is where it is, and it has a height of 2. So then my new wave is going to look like this. Something like that. And then I'll do my blue one. It has also moved 4. 1, 2, 3, 4. So that's right over here. And it has a height of 2, and its length is 4. It's also going to look exactly the same, like this. Okay, and they're still moving toward one another. Then, at 5 seconds, each of them has moved one more space. So my blue one starts here and goes until here, and it has a height of 2, and so then it looks like this. Woo, got wavy at the end there. And my red one here to here with a height of 2, and so it looks like this. And again, we're going to assume that these actually look exactly the same. Okay, now together, I have to look at where are they overlapped. So first of all, from here to here, that's the overlapping region. I need to look in these two pieces of the grid for where they're overlapped. The rest of this is not overlapped, and so it's just the individual wave that's left. Like that. Okay, this middle section here, let's look at the very center. So this is a little bit over 1.5, so it's going to be, when it's together, a little bit over 3. Something like this, we'll say. And then if we look right here at the middle, I've got 1 plus just under 2, so that's just under 3. Something like that. Same thing over here, 1 and just under 2 gets me just under 3. And as I keep doing that, I'm going to find that my middle section looks like this. And so my entire waveform goes up to where it starts to meet in the middle, and then gets this extra little hump in the middle, and then back down. Now for the last one. They have moved one more place each. And so my red one goes from here to here with a height of 2. My blue one goes from here to here with a height of 2. So I'm going to draw it just under so you can still see them both. But they are both in the exact same place. Okay, now when we add them together, since every point is overlapping, we're basically going to take the amplitude of one of them and double it everywhere. Okay, so if we look right in the middle at the apex, this had a height of 2, and so now when we add another height of 2, you get a total of 4. Here, this is about 1.5 and 1.5. That gives us 3, and it's mirrored on the other side. Down here, we have a height of 0 and 0, which gives us a height of 0. Mirrored on the other side. And so it looks something like this. and there's my constructive interference completely overlapped. Now I want to show you one more thing using an actual set of slinkies. So one of the things that we didn't get to do with the wave behavior simulation was what happens when two waves change mediums. So it happens quite often that an incoming wave will be traveling in one sort of medium, let's say the air, and then it will transfer into another type of medium or be transmitted into another type of medium, let's say water. So you're at the beach, you're standing in shallow water, and when you look down, your feet aren't quite where they should be, right? Have you ever had that experience? And that's because when light enters the water, it changes direction, it changes speed, which causes you to see your feet in a different place than you thought they would be. The same thing happens when you put a straw inside a glass of water. It seems like it's bending while it's inside the water, when it's really not. And so that's kind of what we're going to be illustrating here. We're going to be creating a wave in a heavy slinky, in a dense slinky, and it will be transmitted into a light one. And then we're going to check what happens to some of the characteristics of the waves when it does that. This is an example of a wave moving from a heavy medium into a light medium. So we're making a wave right here. Notice the wavelength, notice the amplitude, just try and keep those things in your brain. Okay, it's not very big. Now when it's going to move into the lighter slinky, it's going to change. Look at the size of this one now. Notice that the wavelength has gotten much longer. The amplitude has also gotten a little bit higher, but mostly you notice the wavelength. This happens because it takes less energy to move a light slinky than it does a heavy slinky. So you gave the heavy slinky a certain amount of energy and it moved a certain amount, and then when that energy is transmitted into the lighter slinky, it can move more because it takes less energy to do so. I also want you to take note of this partial reflection here. So when the wave reaches the boundary between the two mediums, between the heavy slinky and the light slinky, it transmits through that boundary into the new medium, but it also reflects back into the original one. This happens because the end of the heavy slinky is a boundary, so boundary behavior kicks in. So because that light slinky is relatively free compared to the heavy slinky, it acts as a free end, and so the reflection is back on the same side. Now we see on this side that wave, once it had reached the end, reflected back on the other side. It came from a fixed end. Now the wave is moving back into the original heavy medium, but notice over here there's a partial reflection back into the light medium as well, and it's reflected on the opposite side it was coming in at. That's because the boundary, when looking from the light medium, is a relative fixed end. It's difficult for that light medium to move the heavy one, and so it reflects back on the opposite side of the medium. Now finally, notice the size of this last piece of wave. Its wavelength has gotten smaller again. Its amplitude though has gotten really small, and that's because by this point friction with the floor has removed so much of the energy that wave had that now it's gotten really small. And the less energy a wave has, the smaller its amplitude.